All right, welcome back, everybody. Let me get the lights down in here. So we're almost to spring break. We're halfway through the semester at this point, which is pretty exciting. And today we're going to be using some of the techniques we've learned to do some processing of textual data and look at how we can analyze a body of text using dictionaries, using file reading, which we started looking at with CSV files, and we'll be looking at Shakespeare's body of work today, and it should be pretty exciting. But first, a few quick announcements. The first reading of the semester that's been out for a few weeks now is due tomorrow. So if you have not started this, you should read it today and respond tomorrow. It shouldn't be too long of a read, much shorter than you'll find in a humanities class. It's a chapter of a popular book, The Ethical Algorithm. And yeah, I think you'll find it fascinating and compelling. The next exercise was posted actually on Tuesday afternoon, I believe. And it's data wrangling. So this is very similar to what you did on Tuesday, looking at using Jupyter notebooks and CSV files, comma-separated values, to read in some data, write some functions to process that data, and similar to how we looked at the difference between row-oriented representations of data versus column-oriented representations, you'll be doing some of that in here, finding averages of columns and things like that. This is not due until the Tuesday after spring break, but I would encourage you to get a jump on this, and if you can knock it out, it's one less thing to worry about. It should move pretty quickly after you've moved through Tuesday's lecture material. Regrade requests, so today we'll be posting the grades for Quiz 2. By and large, it was a strong showing yet again. Really impressed with the work you all are putting in. I think I said this in the very first day of class, but because we hadn't had a quiz yet, it didn't stick. And I'm adding this to the syllabus as well, so it's clear there. But regrade requests need to be made within 72 hours of grades being posted. And this is to encourage and promote everyone to take a deep look at the things that were missed and be sure that you understand why something was wrong. And if we did grade improperly, submit a regrade request within those 72 hours. We've got a really exciting event coming up very soon. This event is primarily targeted towards people who are computer science majors and or considering being a computer science major, but it's open to everybody. It's an optional event, and I want to stress this. There's no real upside to this other than having fun and hacking and potentially replacing your last exercise of the semester. But what it is a hackathon, which let me talk about the workshops first. So the week before the hackathon, we're hosting two tracks, two different workshops you can attend. One is on making a web application. The other is on making a game, a simple 2D game. And to participate in the hackathon the following weekend, we ask that you come to one of these workshops, and that will gain you entry to the hackathon the following weekend. The reason for this is it's a 2-hour tutorial period where you're able to learn a little bit about something that's outside the scope of our course. So we can't really talk about games and web development in the depth that we can in this workshop. And it'll give you a sense to sort of plant some seeds for ideas of what you might think about doing the following weekend. COMP110 is really fun because you're able to pair up with somebody, and we encourage you to work in pairs on a project in the hackathon. And it's an overnight event. So the actual hackathon is on Friday, April 8th, the following weekend. It's from 7 p.m. to 7 a.m., and it's in Sitterson Hall. We've got nap rooms. We have events planned throughout the night. My favorite is the sunrise yoga, but there's a 2 a.m. sprint around campus when it's freezing cold to wake you back up. There's food and drinks and things like that. And so I would encourage you, if you are able to attend both of these, the workshops and the hackathon, and would like to, please do RSVP by Thursday, March 24th. I will be sending out a notice about this later today as well with this information in it. But yeah, I would encourage you to find a friend. It's a great way to meet other people who are going into the major. This is staffed by our wonderful UTAs. I'm there for as long as I can make it. at my advanced age, doing overnight hackathons has become a little bit, it messes up my schedule for a little bit too long the next week, but I'll be there for as much as I can be, and certainly by the time we demo projects at 6 a.m. in the morning that Saturday, I will be there bright and early, and it's a ton of fun. All right, so we'll have more on this soon, but I just want to put this on folks' calendars. It's a really fun event, and it offers the ability to work on a project that's a bit more challenging, a bit more exciting than what we can take on in class. Okay, so what we're going to do today is actually write a program that processes the entirety of Shakespeare's body of work. And this will show you a little bit about how you can work with data in textual files. Right? So the first thing we're going to need to do is actually get all of Shakespeare's text. How do we do that? Well, there's a project called Project Gutenberg, which is the short way of thinking about it is it's an effort to digitize lots of historical works. I believe not only textual works, but also artworks that you can download the full resolution photos of. But we're now focused on Shakespeare. So if you open your browser to bit.ly/Shakespeare-txt, let me see if I can pull this up in a separate tab here. And let's see. That's not doing it. Let me just make this bigger so that the folks online are able to see it. So this is the link, and bit.ly/Shakespeare-txt. And what you'll see is this redirects us to a giant text file, right? So if you scroll down, the first bit of text here is sort of the legal jargon and disclaimer that, where this comes from, who put this together. But you scroll down a little bit and you start to get to the actual sonnets and all of the plays and everything else that Shakespeare created. So what we're going to do with this is we need to save this particular file from the internet down into our workspace so that we can actually read this file into a Python project that we're working on. The easiest way to do that is in Chrome to click the ellipses or to right-click in the browser window. And actually, I think you're going to have to right-click in the browser window. Sorry about that. So if you right-click in the browser window or use 2 fingers to tap on a Mac or Windows, there's a Save As option. Right? And what you'll do is you'll go to your workspace. So in Windows, I'm going to try and find my COMP110 workspace for this semester. And I think I'm actually still working out of this one. And then in that workspace, you can add it to, let's actually go ahead and put this in the lessons directory. So I'm going to go into lessons and just save this as Shakespeare.txt. Right? If that was too small and that was a little bit troublesome to follow along with, let me show you one other way of doing this, which may actually be simpler, which is if you couldn't follow along with that, what I would recommend doing is going into VS Code. And let's just go ahead and set up a blank new file. And let me delete the one that I just made. All right. So in my lessons directory, one of the things I can do is create a new file and call it Shakespeare.txt. And in that blank file, I can just select all. So on Windows, Control-A, on Mac, Command-A, and then copy and paste over. Oops. Not sure why my computer's, there we go. So I selected all the text in my browser and copied and pasted it over, and then I need to be sure to save in VS Code. All right. Good question. So if it pastes all on one line, that will actually be okay for the purposes of what we're about to do, and we might be able to come around and help folks in just a moment with that. For those that it didn't paste all on one line, you'll see that there's 125, almost 125,000, 124,000 lines of text in this. And one of the things I might encourage you to do if yours is not all on one line is just delete some of the text at the end. That's sort of this is the electronic version of the complete works. We don't really need to do this, but there's also some text at the top that we could delete. So at the very top, you can get rid of all this sort of disclaimer jargon texts, and all the way down to, I think the first is the sonnets. So again, this is a little bit, oh yeah, here's a license. There's a lot of legal disclaimer at the top, so you can delete all the way down to line 244, 1609, the sonnets, right? Again, that's all optional. What we're about to do is try and count all of the letters or what are the frequencies of letters that were used in Shakespeare's complete body of works, right? And so if it's all on one line, that's ultimately okay because we'll still be able to count up all of the characters in one line. But if it's multiple lines, you can kind of see, you scroll around and you might find something you're familiar with. I am not a Shakespeare expert, so yeah, I couldn't scroll anywhere and tell you what we're looking at. All right? The key thing that we're taking away here is we're able to take a textual file from the internet, save it, and we're about to write some code to process it. This will be a little bit different than with CSV files, which we just looked at, because this is just a plain text file that has textual English data in it, and we'll be doing something very simplistic with it, just counting up the number of characters of each of the letters in our alphabet. More advanced applications of taking English text and processing it is called natural language processing. This is a field in computer science that is actively researched. And it's how we're now able to have programs that can generate text in response to questions. When you ask Alexa or Google or Siri a question and it needs to send text back to you in an English format or another language, there's really advanced natural language processing techniques going into play. We're going to take a look at something very, very simple, which is just counting up the number of characters. All right. Again, once we get to a good stopping point, we'll have an opportunity for the TAs to come around and help you if you had trouble getting this file going. So the next thing I want to do is set up a Jupyter Notebook. So I'm going to, in Lessons, make a new file named Shakespeare.ipynb. And this should bring up in our Jupyter Notebook a text or a cell that's for a code, but let's go ahead and change this to a markdown cell. So I'm going to convert this cell to markdown and set up a title that is just processing Shakespeare. Yeah, let me try and get these lights down. Surprised. There we go. All right, yeah, thank you for that. Okay. Counting all the letters in Shakespeare's works. All right. And again, in a Jupyter Notebook, if we change a cell to Markdown and use some of the Markdown formatting, like that hash symbol, that gives us a title, so hash symbol processing Shakespeare, and it just gives us a way to document what we're doing in addition to writing some code. And actually, I'm going to go back and edit that, and let's talk about our first step. So the first step is to read each line of the text file into a list of strings. All right? Cool. Now, when you create another cell. I'm actually going to delete the cell that it automatically made for me. Remember, if you hover over a cell, you can add a code or markdown cell. The next type of cell that we're going to add is a code cell. If you already had a markdown cell, remember you can convert back and forth. So if it says markdown in the bottom right corner rather than Python, you can change it to a markdown cell by clicking the ellipses and changing it that way. Okay, so what we need to do is open a file. And as a bit of context here, a file is a sequence of bytes that exists on your computer's storage. And there are different kinds of files, and we're working with a plain text file, which turns out to be one of the easiest kinds of files to work with because it's much simpler than you can imagine music or pictures or other types of files that have really, that you need special programming techniques in order to interpret what's in those files. Whereas with text, we know that we can read characters straight into a string. So the first thing we're going to do here is actually import a type that we need. And I'll explain this in just a moment, but from IO, we will import the text IO wrapper. This is a little bit beyond our concern in COMP110 in terms of what this means and what a wrapper around an IO object might represent. But the way we can think about this for our purposes right now is, as I mentioned, there's different kinds of files that exist in your system. And we know that we're going to be working with a text file, and so this will make it easy to pull strings from that file into the memory of our program. The next thing we're going to do is set up a helper function here. So we're going to define a function, and let's name it readLines. And we're going to give as a parameter the file name that we're reading. And this will be a string. We'll come back and talk about that in just a moment. And what this function is going to do is it's going to return a list of strings, right? Where that list of strings is going to be each line in our file. And again, if for some reason you only had one line in there, but it contained everything, that'll be fine. Your list of strings will just have one entry in it. So let's go ahead and make this a valid skeleton function. Or let's go ahead and add a doc string here. So the doc string is read a text file into a list of strings for each line. Okay. So to make this a valid skeleton function, we can do something such as set up our lines list, which is a list of strings, and make it initially empty, and then return that list. Right? So right out of the gates, we know we've got a valid function definition. Because this is a Jupyter notebook, we could try evaluating this and actually calling it, but I'm going to wait on that for just a moment. Actually, let's go ahead and do it. Let's get a sense of this. So we can set up a variable after this definition. That's something such as Shakespeare's lines, and it's a list of strings, and it is the result of calling read lines. And here's where we actually need to talk about the idea of a file name. So I'm going to do ./Shakespeare.txt. All right. And then the last thing I'm going to do is print Shakespeare's lines. All right. So what's going on with this string Shakespeare.txt? As you all know, every file and every directory on your computer is effectively a string, right? It's a file name or a directory or a folder name. And we can see all those things in our lessons directory, right? So in our lessons directory, that's where I set up Shakespeare.txt. That's where all of the text from Shakespeare's works are. And then Shakespeare.ipynb is the actual notebook. What this / is representing is look in the current directory. We're not going to spend a lot of time talking about sort of these, what we call this a file path, because there are ways that if we needed to say, hey, go up one directory or go up two directories and then look in some other directory, there are ways of doing that with other annotations. Little like ... means go up a directory. And you'll actually see this in the next exercise, data wrangling, but it's not worth getting hung up on here, right? So when we actually evaluate this, you'll notice that at the very end, we see that an empty list is printed out, and we expect that. So now what we need to do is actually read this file in, right? So what we need first is a way to access that file, to address it. We need a handle on that file. So let's set up a file handle. And this is going to be a text IO wrapper type. Right? And what we're going to do is open a file. So with files, you tend to open them and close them. Opening a file just means, hey, you're asking your operating system, hey, give me access to some files in storage. And what we're going to open is the file name parameter, right? So we pass in, when we call this function read lines, we're passing in Shakespeare.txt. That's what's causing the file name parameter to be set to that, and we're opening, effectively Shakespeare.txt in this example. But this function will be generic such that if we wanted to go read other files or use it elsewhere, we easily could. The second argument that we provide to open is kind of funny. And if you hover over the open, if you hover over the function open, you'll get some helper text in VS Code, and you scroll down, and you'll notice that it talks about the mode. And there are different modes we can open a file in. We can open a file for reading. We can open a file for writing. We're opening this file to read it, right? So we're going to use just the string R here. Right? That's a strange convention that goes all the way back to the 70s that's been followed ever since. But the idea is you don't always want to read a file. We might want to write and save things back to our computer. There are easy ways of doing that. For now, we want to read this file. 1 second here. We're not going to worry about closing. All right. So the next thing, now that we have this file handle, what's really neat about this text IO wrapper type in having opened a text file is we can actually read line by line. And we can do this because this is a file is effectively a sequence of lines, right? One line after the other after the other. And in fact, when we look at this file, VS Code is numbering these lines for us. It's starting from 1, but we'll ignore that. So we can actually write a for loop. So for line in file handle. And what this for in loop is going to do is it's going to read the next line from the file, store it in a string whose variable name is line, and then we can use that, right? So why don't we go ahead and say lines.append line. And so now if we run this, we're going to read the entirety. If this works, we should be reading the entirety of Shakespeare's works into a list, and it's all getting printed out. But you'll notice that, well, VS Code is trying to, normally it says, hey, you've got too much output. We're not even going to try. Oh, there it goes. So down at the very bottom, it says the output exceeds the size limit. Let me bring this back up. And so what we've got is you can see that the first lines here are 1609, this \n. We talked about it very briefly earlier in the semester. It means a new line or a blank line. And after each of the entries, you see that this new line is saying there's an enter at the end of that line. We probably don't want that to be there, that \n. So we can do a little bit of pre-processing on this. All right? So in this for loop, we can say line is assigned line.strip. Right? And when you strip a string, what it means is if there's spaces or new lines on either side, at the start of the string or the end of the string, it removes those. So if I try rerunning this cell, you'll notice that all those \n's disappeared because they're what we call white space. You don't see them, and the strip method of a string causes it to go away. One other thing we'll do very quickly, and then I'm actually going to pause and we'll have a minute for the TAs to circulate around, and I'll post something in Course.Care for folks to check in, is we probably don't want there to be uppercase characters, right? The goal that we're trying to work against is we want to count the number of letters and the frequencies with which letters are used. So why don't we change all of our strings to lowercase? So we can also say line is assigned line dot lower. Right? And so if we rerun this, notice that now all of the characters are are converted into lowercase. And if you think about what we just did, it's pretty incredible, right? We wrote a simple, 5 or 6 line function here that read in the entirety of a file with 125,000 lines in it, all of Shakespeare's entire body of work, more than any of us have read, I would posit, and changed every letter to lowercase, took out new lines, and we've got it all in one giant list that, if we wanted to print the length of this list, let's see how many lines we've got in it. Oops. We now have a list of strings that has 124,000 items in it, right? So this is, I think, the largest body of or data structure we've worked with in this course at this point. And by computer science standards, this is still pretty tiny. It's just one person's corpus of work. All right, so let's pause here for a moment. I'm going to post into Course.Care something to check in on. And check in on that. If you're having trouble saving the file or getting this going, raise your hand and the TAs and I can come help you. We'll spend just a few minutes being sure we're all at the same point here. All right, looks like 57 people have checked in. So there's a message to respond to on Course.Care and the open discussion. Numbers continuing to go up. One more minute, and we'll continue from here. All right. Seems like we're almost there. Just one more minute. We'll resume at 10 a.m. And if you're not able to follow along for some reason, don't stress. Come by office hours, and you should still be able to keep writing the code. Even if you can't run it, you can see what's going on, and it'll probably be something small. All right. As I mentioned, if for some reason you get stuck or hung up on something, we'll have a few other opportunities to come around, but just following along as best as possible is totally fine. We're not turning anything in from this today or anything like that. And I should also mention that this is different. The next assignment, exercise 7, is much more like Tuesday's lecture than this one. This one is sort of a, let's step back and look at some of the interesting, crazy things we can do with what we've learned so far. And here we're seeing a list, we're seeing a for-in loop, we're learning something new with being able to open a file and read it into our programs. And yeah, we have now in memory, like, the memory diagram for this would be pretty insane, right? You've got a list with 124,000 elements in it, and now we want to go do something interesting with that. So let's add one more code listing after this, and I want to show you, and I'll just make a comment here, example of slice notation. All right. We're not going to spend much time or expect, slices are something that are kind of unique and special to Python. And there's some other languages that have it too, as well, but just to show you something kind of neat, if we wanted to just look at the first few items of this list, there's this special syntax that looks like subscription, right? So if I were to just print Shakespeare lines, and then in the subscription notation, if we're thinking about, if we wanted to look at just one line, right? Line 0 is 1609, line 2 is the sonnets, or index 2 is the sonnets, index 3 is empty, index 4 is by William Shakespeare. You kind of get the point, right? Well, what if we wanted to look at just a slice of we've got 124,000 items. What if we wanted to look at the first few of them? You can do something like 0 and then colon and then 5. And you'll notice that that gives us a slice or a sublist of this that's the first 5 elements of it from indices 0 through 4. And so we can kind of get a sense, okay, yeah, it looks like we've read this file in, we've converted every line to lowercase. Let's go do something with this data that we've got. So let's add a markdown file and say the next step of our analysis is to count all of the letters in Shakespeare's complete body of work. All right. And I'll evaluate that, and as soon as if you press Shift-Enter and go to the next cell, if you were previously in a Markdown cell, it keeps you in a Markdown cell. So let's convert this back to a code cell so that after you've got some notes about what we're doing here, we're counting all the letters up. We've got another code cell after it. We know that because in the bottom right of that cell, we've got Python showing, and we can write some additional code. So what's a good tool for counting things such as letters that we've got in our toolbox? Or what's a data structure that we might use to count? I'm hearing louder. Dictionaries, yes. So we're going to use a dictionary to count the number of times we see each letter. And the key of the dictionary will be the letter. The value will be the number of times we've encountered that letter as we're processing this body of work. Before we actually get into processing all these lines and writing a function to do that, I want to write a simpler helper function that emphasizes, and actually I think I'm going to turn it over to you to write this function. So the goal here is to write a function named count. Actually, let's name this function tally. And what we're going to do is, given a dictionary, given a reference to a dictionary and a key, increase the value stored at the key by 1 if key exists. Otherwise, set key's initial value to 0. Okay. And this is a function that returns none. It's a procedure. Right? So I want you to try using this specification And let's spend just a few minutes on this. We'll be circulating around and can continue helping folks. And see if you can try and implement the basis of a function named tally. You give it a dictionary, and you give it a key, and it will increase the value of that key by 1 if that key already exists in the dictionary. Otherwise, it will set that key's initial value to 1. So see if you can try writing this function. This is a lot like the quiz function writing problems that we encounter. And we'll come back at 10:10 to work through this together. All right, it's sounding pretty quiet in here, so I might go ahead and get moving on this. So when we see a definition like this, the first thing we want to do is get the signature correct. So the name of this function is tally. And we're told that it's given a reference to a dictionary. That means we need a parameter whose type is dictionary. So I might call this, you can call it whatever you'd like. I might call this counts. And the type is a dictionary where the keys are strings because we're going to be counting the letters. And the values are ints. That will be our counts, or the tally for the number of times we've seen it. And then we'll pass in a key, which is also going to be a string. And this is a function that we said returns none. So we still have more work to do, but because it's a function that returns none, this is actually a valid function definition. If we put in 3 ellipses, we still need to, of course, actually update our dictionary counter. But this is the correct signature line, and we can proceed from here. So let's go ahead and add a docstring. Mutate counts by incrementing key, by incrementing value stored at key by 1. And that's actually pretty descriptive because we're thinking of this as like, a tally that you might keep on a sheet of paper where each time you see a new letter, you would write down that letter in the first tally mark. each time you see another letter, you're increasing that tally by 1. Right, so we're counting up the letters. This function is a helper function that will count one additional letter or one additional tally entry to a given key. So how do we test whether a key is in a dictionary? Well, we can test if key in counts, right? Because I named my parameter counts. If your parameter name was different, of course, you'd be testing whether that was in the dictionary you named it. And if so, then what we're going to do is say, okay, update the counts key entry by 1, right? Otherwise, counts key is assigned 1 initially. And so now we've got what seems to be a reasonable implementation here. If the key is in this dictionary already, we're going to increment the value stored at that key by 1 using our relative reassignment operator. Otherwise, what we're going to do is just initialize it to 1 because it's the first time we've seen that key or that letter. All right. So we're building this little helper function because this is something that you always have to do. When you're counting up using a dictionary, you kind of always have to know, have you already seen this before? Okay, yeah, let's increment. Otherwise, no, let's set it to 1. So now let's actually write a function that can take in our list of lines or a list of strings and produce a dictionary with all of those counts. We'll work through this together. So let's define another function, which is def count letters. And what we are going to have as input here, or as our parameter, is a list of strings, right? So these are going to be lines, which is a list of strings. And it's going to return a dictionary where our key type is string, it's the letter that we're counting, and our value type is integer. And as a docstring, we can say count the frequency of all letters in a list of strings. Now, because this is a function that says it returns a dictionary where the key type is string and the value type is integer, we don't have a valid function, right? So let's make this a valid skeleton function before we actually worry about our algorithm here and set up maybe a variable named counts that might be a type dictionary string to int. And it's initially an empty dictionary, so we use the dictionary literal where we have empty curly braces, and we can return counts at the end. So this is now a valid skeleton function. We've set up the variable that we're going to be building up as our result. And again, what we're trying to do is read each line, move through every character in every line, and add each letter to this counts, tallying up 1 by 1. Each time we see a new letter, we increment the count of that letter by 1. So let's try it. Actually, this is another good point to try turning it over to you for a test pass at this. So try looping through each line in lines, then loop through each char in the line, add that char, or tally up, I should say. Oh no, let me make this a little bit brighter here. Tally that char in the counts dictionary. And to get a sense of whether or not this is working, we can bring this example closer to complete, and let's actually print the result after this function definition of calling count letters with Shakespeare's lines. All right, and so when I evaluate this, you see that I've currently got the empty dictionary here is the result, but if you try implementing this nested loop, where you loop through each line, and then for each line, you loop through each character in the line, and then you tally up that character with the counts dictionary using that function we just defined. You should see a dictionary where the keys are all characters, and the number associated with them is the number of times that character was encountered in the text. So let's spend 3 or 4 minutes trying to work through this, and we can come around and help you as well. And if you want a little extra challenge, you can try testing whether or not that letter is actually, or whether or not that character is actually a letter, meaning something that's A through Z, and not counting things like commas and periods and other punctuation and numbers. Two more minutes on this, and we'll work through it together. If you need help, raise a hand. Otherwise, compare notes with your neighbor. All right. So this is an example of a place where the for in loops are really handy, right? So we could do this as while loops, set up two while loops, two different counter variables, but this is a place where we're scanning the entirety. We want to move from the start of our file, all of the lines from start to finish, and then in each of those lines, we move from the very first character through the very last character, all in order. Nothing really special or magical about the way we're iterating through this. So a for in loop works great in both instances. So we can say for line in lines, for care in line. And then we can use our helper function that we set up, tally. We can tally. And what are we tallying into? The dictionary named counts, and we're tallying this care, right? That's the key. And you'll notice that this is actually an example of a place where passing by reference is really handy. Notice we're not doing anything with there's no return value to tally. It's a function that returns none, right? But because we're giving a reference to this counts dictionary, and in that tally function, we're mutating that dictionary, this is still having impact on the counts dictionary that we set up as empty initially in count letters. So by the time we do return counts and we print it out, we should see we see the number 1 came up, or the character 1 came up 892 times. The character S came up 248,000 times. The letter H 236,000 times. And you can see that we've effectively counted up or tallied up all of the characters in Shakespeare's works in this way. Let me see if I can get this all to fit. I can almost get it. Now we still have a little bit more work to do, because our purpose here is really to count the letters. And we're getting numbers, we're getting punctuations, like there's 8,800 exclamation points in Shakespeare's works, versus, I wonder how many periods, let's see if I can find that. I'm not seeing period on there. It's somewhere in there. Does anyone see it? Oh, there it is, 77,000. Yeah, so almost an order of magnitude more times, Shakespeare used a period rather than an exclamation point. Anyway, we really don't want that data in here, so we want to filter it out. And one of the ways that we can do that is we can test whether this character is within the range of A through Z. And I want to show you two ways of doing this. First, what we learned earlier in the semester, if char is greater than or equal to the character A, and char is less than or equal to the character Z, we could tally it up this way, right? So if I ran this again, we would see that after testing, now we've narrowed it down to just our alphabetical letters, because we can compare using string comparisons, two different letters, and if we write a complex Boolean that says if it's within this range of A to Z, then it's a letter within our alphabet, and we've narrowed it down in this way. So we've effectively filtered out some of the noisy data about punctuation that we really weren't that interested in this example. Earlier, we looked at two methods of strings. If I scroll back up, and you can keep yours where you're at, the ability to strip a string, to remove white space from around the start or the end of it, to change a string to lowercase. There's actually a built-in method in all strings, which means the character has it as well, where we could test if char.is alpha, right, if it's alphabetical. And this has the same implementation of what we just did, so that we should see the same result here. And that's one other way of doing it. Both ways are fine. What's kind of neat about is alpha is it will test all of the characters in a string that's longer than just one character. So if you had a complete line, it would return true if everything was a character or everything was a letter, and there were no other types of spaces, and false otherwise. There are a few of these types of helpers. So I think there's numeric, and is punctuation. I don't remember them all, but they're in the Python reference if you ever wanted to test for certain characters being in certain classes of characters. All right, so we've got all these tallied up, but it's kind of hard to internalize or actually rationalize this data, right? It's hard to reason about it because it's just a dictionary in Python. We know that visualizations are more helpful than just things like this, where we just see some text. So why don't we set up a visualization of this using PyChart? If you're seeing an infinite loop, I would suggest trying to restart the kernel with the restart button and seeing if that helps fix it. Otherwise, come work with us in office hours and just follow along with this last bit. So let's add one more markdown cell. So I'm going to add a markdown cell and just document that we are trying to visualize with a bar chart this data about character frequencies. All right, I'll add another cell below that and be sure that the next cell is actually code. So I'm going to change to code cell. All right. Now this last part requires a library called matplotlib, which is very popular for plotting mathematical or data visualizations. This should have been installed at the very beginning of the semester when you set up your computer, but there's some chance that something went wrong during that process and it might not be installed. If so, you would have seen this also on Tuesday, and maybe you came in to work with us in office hours to get it fixed. Otherwise, come work with us, and we can help you get that fixed in office hours. And you'll want this for some of the exercises we have coming up, where you are trying to visualize the data that we've represented. So what we can do is from matplotlib import pyplot. Right? Oops, plotlib, not ploblib. Matplotlib. And this is short for mathematics plotting library. And Python plotting is the module within it. If you evaluate this, and actually before we even think about this any further, let's be sure to save. So one of the things, so Control S on Windows, Command S on Mac. I should have been saying this all along. One of the things that can be, that is hard to remember when you're working in a Jupyter notebook is to keep saving your work. And that's because while your kernel is running, you're still able to see your program actually run and see the results without saving. But if you don't save, if for some reason you were to crash your computer or something like that, or even submit your work to Gradescope, your work wouldn't actually transmit to Gradescope until you save the file. So be sure you're saving judiciously as you're working in Jupyter Notebooks. So if you evaluated this cell, you won't see any output yet, but if you saw an error, that means we need to get Matplotlib installed on your machine. If you didn't, then you should be good to go. Okay? So this is a library that is a very popular third-party library, and it's got lots of different options for creating different visualizations, and there's no way to memorize all of the different method calls that you need to make. So whenever you're going to make a visualization, typically you're searching for something you did before that you could reuse, or you're going out to the internet and looking up, hey, what kinds of visualizations could I make and how do I do this? So there's just some things that we need to do to set up this PyPlot. So in this case, we're going to set up a title. And the title of this will be Frequencies of Letters in Shakespeare. All right. And we're going to set up an X label. That is the letters. And PyPlot Y label, that is the counts or the frequencies. And then what we're going to do is set up just two simple variables so that we know what we're actually working with for our labels and for our values. All right, so our labels is going to be a list of strings. That is a list of the keys. So we've got, we actually need to go back and do something in just a moment. Actually, let's put a pause here. So we'll just make this the empty list for now and say to do list of keys. Okay, so one of the things that I failed to do in the previous code block is actually set up, and let me actually just clear my output so this might all show up. Cool. All I did was clear my output. In the previous code cell, what we did was we printed the result of counting letters, but we didn't store that result in a variable. We really want that in a variable so that we can use those counts, that dictionary later on. So let's set up a variable named Shakespeare counts. And it's a dictionary from string to int, so this will be the result of calling count letters. And if we wanted, we could print this variable and see the same output we were seeing before. So if I evaluated this cell again, we would see all those frequencies being printed out as a dictionary literal format. For the time being, actually, I do need to run this. So let me just give you one more second here. So the point of what we just did, right, is we need a variable that references this dictionary that we can then use later in our program when we want to go and plot those values. Previously, we just printed them out and didn't store them in a variable. All right, so I'm going to run this cell. And we see, there we go. There's all my frequencies. And now we've got a variable who is named Shakespeare's counts. And a special method of dictionaries that we haven't talked about is you can say dictionary name dot keys, and that will give you a sequence of the keys. It doesn't actually give you a list, so that's why we're using the list constructor to convert that into a list. The actual type of that is a little bit beyond our concern, but know that this is just saying after this, if we were to actually go print this, which we could try, so I could say print labels. Notice we've just got a list, and ignore the plot that showed up below. We've just got a list of all these individual characters, all right? We want to do the same thing with our values. So those are our labels, and our values are a list of ints, and it's a list of Shakespeare's counts dot values. All right? And if I were to print the values, we would see that that's also just a list of integers that are the corresponding values with those letters. Cool. So let's actually, now you'll notice if you were to scroll down and you see this plot show up, there's nothing plotted yet, so we need to actually set this table or assign these values and these labels to a bar chart. So we can do that with pyplot.bar. And if you see red squiggly underlines here, you can ignore them. This is one of the downsides to working with a third-party library is sometimes they don't have all of the function names set up in the way that you would want them to work in VS Code, so that it says it doesn't know that bar actually exists, but it does. And we know that it does because when we actually ran that code, we can see the bar chart down below. I'm going to leave this code here for just one more second to be sure you're able to follow along. Yep. So yeah, let me scroll back up to the part just above that set up this Shakespeare counts. Yeah, so this should have all of it. So rather than printing out the result of calling count letters, we stored that into a dictionary. And you have to be sure to reevaluate that cell once you're done with it so that that variable exists. And then we used a third-party library called pyplot to produce a bar chart. And I just want to impress upon you, if I press this run all button, this restarts everything from the start, and boom, it's done. And in that amount of time, the program read in the entirety of Shakespeare's corpus of work, counted all of the letters, including picking out the ones that were punctuations and things like that, and generated a bar chart down below. And that level of computation, that power, which we're barely scratching the surface of here, like if you think about what that would take in terms of effort as a human, it would be so painfully tedious and mind-numbing that you could spend a year doing it and probably have some errors and not enjoy life at all. And here, in just a few seconds, we were able to run a program that took us only less than an hour to write to do this work for us. And so it's examples like these that I think really demonstrate some of the power of computation that you have available when you can write programs. There's one other thing that we might do to improve this program. You'll notice that the x-axis has characters in the order that we encountered them in Shakespeare's works. So the is the first word, that's why THE are the first 3 characters. And then it's these sonnets, but because N is a duplicate, and then E is a duplicate, and T is a duplicate, we've already seen those characters before. Anyway, it goes on, but you kind of see by Willem. And then finally we get down to the least frequent characters. Z, X, Q, and J are very infrequently used in Shakespeare. It probably makes sense to try and order these in a way that is more valuable or more easy to understand. So let me try something right here. So Shakespeare's counts is assigned sorted Shakespeare's counts. And I'm going to do some magic here for just one sec. All right. So this line of code that I added just above, which reassigns Shakespeare's counts to be this ordered dictionary, is doing some, has 3 steps to it, right? The first step is we're getting all of the items out of our dictionary. And what this items is doing is it's setting up, getting us a list of tuples. And we'll talk about what tuples are in just one moment. We didn't get to talk about them a few weeks ago, so we'll talk about them today. There's this built-in method in Python called sorted that, if you give it a list of things that are unsorted, it will put them in order for you. And there's some other options that can control whether you want to sort ascending or descending. Here, because we have a list of strings as the first item of our tuple, which is our key, it's sorting them in ascending alphabetical order just by default. And then we're turning all of that back into a dictionary so that we have those tuples put back into a dictionary, but in sorted order. And so here we can get a much nicer visualization where we've got the letters of our alphabet all in the order that we would expect in their relative frequencies. One of the interesting things you could do here is download a list of Wordle's valid words. So just like these Shakespeare's corpus is available here. If you were to go to bit.ly/wordlewords, Wordle-words, you get the list of all the 5-letter words that are valid words in Wordle in a plain text file. You could save those into a text file in VS Code and do the same analysis and know what letters have common frequencies in Wordle. I'm not going to do that so that I can talk a little bit about tuples to close us out. So we didn't quite get to talk about sequences, and sequences are this concept that we've encountered many times. So lists are sequences, strings are sequences, and this is an abstract data type, meaning there are many things that we can think of as sequences, and they have these special properties to them, right? So the special properties are that we have an ordered sequence of items that are 0 indexed, right? And we can use subscription notation to access the items of a sequence. We've seen string and list, and today I want to talk about tuple. We looked at range briefly previously. So tuples are a slightly more constrained, but also more efficient list of characters, or a list of values. What's neat about them versus a list is that we can combine different types, right? So tuples are a specific fixed length sequence that can be of mixed types. They don't have to be of mixed types, but they can be. When we say fixed length sequence, that means once you have a tuple, you can't add anything to it. You also can't change anything that's in it. We call these an immutable data structure. They're an immutable sequence. You can set up a tuple, and once you have that tuple, those are its values. If you want to change a value, what you effectively have to do is create a new tuple with the different values and then reassign whatever variable you had previously. The way that you specify the type of a tuple is with the keyword tuple, and then in our square brackets, we have the types that are each item in that tuple. So kind of like a dictionary where you have a key type specified and a value type specified, here we're saying, tuple at index 0, the first item in this tuple is going to have whatever the type is first, the second type second, and so on. So here are 3 different examples you could imagine. And we also typically give names to these things. So if you use tuples in a program, they're very common in games when you're thinking about having 2D points or 3D points in a game. You'll typically set up a variable that's a global, effectively like a constant, that says, hey, the type tuple float and float is now going to be called point2D, or we can use the name point2D to refer to this type where a tuple has 2 floats in it. When you're working with image data, like photos and in pictures, colors in computer programs are typically represented with 3 colors, amount red, green, and blue. And so you would have a tuple with 3 integers in it, right? But you could also imagine mixing types where you could have a player that has a tuple of a string and a float. And so if you look down at the bottom where we have Baycut, that's type player. And the way we specify tuples is kind of funny. Rather than using square brackets like lists or curly braces like dictionaries, we use parentheses in Python to say, hey, this is a tuple. This can be confusing because the place where you're used to seeing parentheses is typically in function calls, right? So these are 2 different uses of parentheses. And one of the reasons why we don't really emphasize the use of tuples is because they're a little bit harder to read as an early programmer. But you do see them very commonly in the Python programming language. What's neat about them is this ability to combine types and to know that you have a specific number of values always in a given tuple. Right? With a list, you don't have any guarantee that it has 3 items in it or 4 items in it. Right? You have to always check, hey, does this item, or is the length long enough for this index to actually exist? Whereas with a tuple, you have a guarantee. Like with this color tuple, you know that there's an item at index 0, 1, and 2, and you know that those types are all integers. Right? So the bottom here shows you tuple literals, and there's some other really interesting things you can do with them. So why do I mention that? Well, this example that we just ended on, where we took Shakespeare's counts.items, I want to dig into that just a little bit further. So I'm actually going to add one more code cell down below. And if we look at Shakespeare's counts, and remember when we have a Jupyter Notebook cell where we evaluate something that's an expression, whatever the last expression in that cell is gets printed down below, and so we see here is that dictionary literal. But what I just mentioned is we use this .items method. And notice that what this gave us was, ignore the dictionary items part, but look at how we have a list, and then we have a list of tuples, right? Where the first tuple is our key A and the value associated with it, that's the integer. And so the way that we were able to sort all of our keys and values is first we got this list of tuples, then we sorted this list of tuples using the sorted built-in function. So previously, if we had done this, we would have seen TH and E as our first set of tuples. And then we took that list that was generated and put it back into a dictionary. So there's one other way that we can create a dictionary that I'll show you just to close out. So we can have a dictionary, and if we had, say, a list of tuples where our first one was just say spring and 110 and break and I don't know, making this up on the fly, a large number. Another way of constructing a dictionary is by giving a list of tuples where each tuple has a string type as the first value and a has your key type as the first value. So in this case, it's a string, and your value type would be the second entry in each of these tuples. And so there's ways of effectively saying, hey, dictionary, give me a list of tuples, and then going back into a dictionary format where you take those tuples and bring them back together and put them into a key value dictionary. And so we're seeing both of those things here. So if we wanted to, we could have typed just this list, and actually this will be the last note that we make. So this is going to be example tuples is a list of tuple, and our first value type is string, and our second value type is int, right? And then if we wanted to see the dictionary from tuples, we could have a dictionary where string and integer are the key and value types, and we can use the dictionary constructor and give it the list of tuples. And we can print that out. So this was, again, a little bit more detail than you need to know for the purposes of 110, but just to understand what was going on and how we were able to sort that dictionary was we broke it down into its items. So you can ask a dictionary for its items. That gives you a list of tuples. We can then sort a list using Python's built-in sorted. And then we can take that sorted list of tuples and put it back into a dictionary. And that was what was going on online, on the line where we had this series of function calls. All right, that's all we've got for today. Hope you all have a wonderful spring break, and we'll see you back here after some much needed rest and rejuvenation. Yep. All right, welcome back everybody. Today we will be taking some of the concepts that we've learned over the course of the semester, which we're now over halfway through, believe it or not, and bring them together to do some more data analysis in a Jupyter notebook, looking at a slightly different kind of analysis than we've been looking at so far this week, where you processed a CSV on Tuesday. But before we get into analyzing textual data, let's talk about a few quick announcements. First, the initial reading of the semester is a chapter out of the ethical algorithm, and it's a great introduction to how to conceptualize algorithms and think about them at a broader scope than we talk about typically in class. As a reminder, this is due tomorrow. This has been out a few weeks. If you haven't started yet, I would encourage reading today. It's a pretty quick read. It's one chapter in a popular best-selling book, and responding to the couple of short essays and guided reading questions while you're doing it or sometime tomorrow. The next exercise was posted earlier this week. It's data wrangling. It looks a lot like the type of analysis, or it's a continuation of the analysis we began on Tuesday, where we're taking a CSV file and processing it. It's due after spring break, but I would encourage you to get a jump on this and try and knock it out, so that way there's nothing to worry about. But there will be a few days after spring break, but do know that if you're thinking, I'm not going to worry about this until after spring break, you're probably not the only one. So wait times may be longer after spring break, but that's due 2 weeks from now, effectively. One of the things I mentioned the very first day of class, but because we hadn't had any quizzes yet, I don't think really sunk in, and people have been caught off guard by this, but regrade requests have, oops, that should have said 3 days, not hours. Yeah, you really got to get on it. So you've got 3 days. I don't know how someone in the previous section, everyone was still asleep, I guess. No one noticed that. 3 days after grades are posted to submit regrade requests. So we're going to have quiz 2 out. The scores were awesome and pretty healthy across the board. That'll go out later today. There'll be 3 days to submit your regrade requests. The reason why we put a time period on this is because the best time to move through the feedback that you received and try to understand where things went wrong was very soon after, as soon as possible, not at the end of the semester when you're reviewing for the final or something like that. So when the email announcement goes out that your scores are released, I would encourage you to look through it. Where there are things that you got wrong, understand why you got wrong, what was wrong about them. As I mentioned last week or 2 weeks ago, we can't arbit regrade requests in office hours. Just submit a regrade request. You pull up the question in GradeScope and say, hey, I think this was graded improperly. Here's why I think it was graded improperly. If you're wondering why something was graded the way that it was and you have questions about why was this correct, come talk to us in office hours. So get those in by Sunday. And the next announcement is a really exciting one. We're hosting COMP110. This is an optional event where that is a slightly different format this year than previous years, but I'm excited for it. I think it's going to be fantastic. So this is an event that's spread out across 2 weekends. In the very first weekend, so Friday, April 1st, we'll have 2 workshops that are optional. You choose which one is more interesting to you. One will be on web development. The other one will be on game development. And again, this is all entirely optional, but it's highly encouraged for folks who are considering majoring or who are majoring, or folks who are just looking for an extra challenge. You do need to be able to make both of these things in order to attend the full hackathon, which is the following Friday, starting at 7 p.m. and going until 7 a.m. the next morning. And over the course of that period, you'll be working with a teammate on some project, a game of your design, a web application of your design. You'll be surrounded by a lively group of undergraduate teaching assistants who can help you overcome some of the hurdles with that. There's a lot of fun eventing that takes place and is designed to keep everyone awake and engaged, such as a late night fun run, sunrise yoga, that's probably my favorite event, an ice cream station, there will be food, and things like this. If you're planning to attend, please RSVP by March 24th, and I'll send out an email with this information as well. We need a head count for the amount of food to buy and the number of shirts to order. This is, again, an entirely optional event. It's mostly for just meeting other people who are also excited about continuing on in computer science, getting a chance to work on a project that's a little bit larger in scope than what we take on in COMP110, and to just have a fun time programming overnight, which I imagine most of you can't think of anything more exciting to do on a Friday night. I know I certainly can't. So yeah, we'll have more information about this announced soon. Okay, today what we're going to be looking at is natural language processing in a very simplistic form, right? So natural language processing is an entire subfield in computer science that is devoted to taking human spoken written language and trying to compute with it. Today we'll be looking at Shakespeare's corpus of work, which represents a pretty wide range of titles and poems and sonnets and plays that he wrote over the course of his career. And the first thing that we need to do is actually get this text onto our computer. So in this first step, I'm going to ask you to open a web browser to bit.ly/Shakespeare-txt. Uh-oh, spelled it wrong. Missed an E there. And that will quickly redirect you to this plain text file that's pretty large, right? And the first bits of this file are sort of the legal jargon saying, hey, this is out of Project Gutenberg. Project Gutenberg is a very cool project that was in the, I think, 90s and early 2000s, maybe it's still going on, that tried to digitize the works of the classics so that they're freely available. And here we have all of Shakespeare's work available in textual form. So if you scroll to a random point, I don't know enough about Shakespeare to know what Pembroke, Salisbury, and Mellon are from, but one of his works is here, and all of the works over the course of the whole corpus are also here. So if you search for your favorite character, like Demetrius, I can't spell it right. This is a horrible demo. Oh, it's just taking that long. I actually did spell it right. It's just that searching in Chrome takes so long to actually do the text search because there's enough text here. Anyway, we've got Cleopatra and Antony. You can believe me that this is the entire work. So how do we actually get this file into our VS Code? There are a few ways. I think the easiest way is probably just to open VS Code and copy and paste it for our purposes and following along today. Once you're more comfortable, what I want to point out is that it's very simple to right-click on the back of a web page and choose the Save As option and save that file somewhere on your computer. But for our purposes in following along today, I think the simplest mechanism is just to open up, and we'll put this right in our lessons directory, a new file, name it Shakespeare.txt, and you can select all text, either through the Edit menu, Edit Select All, or Control-A on Windows, Command-A on Mac, and then copy that, and then paste it. So I Controlled-C in Chrome and Controlled-V over in VS Code, but I just, or Edit, Copy, Edit, Paste. Oops, and we've got 124,000 lines of text. If you want, you can delete some of this jargon disclaimer. This isn't actually Shakespeare's work. I don't think it actually matters because there's so much other text that it won't dramatically impact the rest of it. But you can scroll around and see, yeah, sure enough, this is everything that we had there now in VS Code. And this file gives us the ability to start working with it and reading a file from our computer. All right? If you had any problems opening the file, copying and pasting it over, we'll be able to come around in just a minute to help with that. But let's go ahead and set up a Jupyter notebook. All right, so I'm going to open up a new file in lessons, and let's just call this Shakespeare.ipynb. So a Jupyter notebook, as we've been starting to look at, is an exciting way to do data analysis and what we call interactive programming. We have two different types of cells. This first cell, it gave us a Python cell, but we really want to start out with a Markdown cell, so I'm going to click my ellipses and convert this cell to Markdown. You could also delete the cell and then add a Markdown cell either way. So if I double-click that Markdown cell, I can now enter in some text, and we'll do quantifying Shakespeare. in this notebook, we will find the frequencies with which Shakespeare words used letters. So the point of what we're going to do today, as I mentioned, is very simple natural language processing. In fact, this is as elementary as it gets. We're going to be taking all of the text and counting up the number of times individual letters were written and used by Shakespeare to figure out what letters were most common or least common, and maybe this can guide our Wordle strategies. We might also compare it to Wordle's list using a very similar analysis and see where the differences are between 5-letter words and the entire English language as used by Shakespeare at that point in time. So we've got some work to do. And just to sort of zoom out a little bit and talk about natural language processing, this is a very simple example, but of course, organizations like Google, Microsoft, Facebook, and Apple are all doing, and Amazon are all doing this at massive scales. There are lots of other companies doing this as well. Taking all of the text of the internet, feeding that into programs that analyze it, look at frequencies, and try and build neural networks. This is how things such as Siri and Alexa are able to have kind of quasi-conversations with you. We're still in the early days of it, of course. There are places where Siri and Alexa are not very helpful at all. But the fact that we're able to create and generate language that we can interact with is pretty fantastic, and it's amazing to have seen the progress natural language processing has made over the years. So the first thing we need to do is actually read that file in. We've got this file here, right? We actually want to read this file in to our Jupyter Notebook and get all of this text in memory as strings. The first thing we want to do is figure out how do we open a file. Well, I'm going to set up an import here. So from IO import text IO wrapper. And you'll notice that I'm not getting any syntax highlighting. That's because I'm still in a markdown cell. For whatever reason, VS Code, after you evaluate a markdown cell, if you use the Shift-Enter shortcut to move to a new cell, it will keep using the same type as you had before. So I need to convert this back to a Python cell. So I'm going to change cell to code. Right? And so then you get the syntax highlighting by changing it back to code, and you can go back and forth between markdown and code, of course. What we've just imported is the type of an object we're going to use. It's a little bit beyond our concern, but basically, when we read files from our computer, there are different kinds of files that we might be working with. And here we're working with just a plain text file. It's just strings in here, right? And that's pretty different from if we tried to open up a picture and look at the data of it. It wouldn't be text, right? It's binary values that are encoding colors in ways that we couldn't easily read unless we tried to visualize it as an image. But this is just saying we're about to work with some text, and we'll use this as a type of variable here soon. When we open a text file, we're going to get back a text IO wrapper. So let's set up a function that will help us read a file in. So I'm going to name this read file. And we're going to give it a file name as a parameter, which is a string. What it's going to do for us is return a list of string values. Right? So given the name of a file, return a list of its lines. And this isn't quite a valid function yet. Because we said this returns a list of strings, we can go ahead and turn this into a skeleton function by following our strategy of saying, OK, let's set up our lines as a list of string values. That is initially empty, and return lines. And of course, we have more work to do. More work, right? In between these things. But now we have a valid function. And if we wanted to, in this Jupyter cell, we could try evaluating this function and giving a file name. Right? So again, the purpose of this is we're going to give it the name of this file, shakespeare.txt. And it's going to produce to us and return back a list that has all 120,000 lines of text from that file that we can now work with in memory. All right? So let's try setting up a variable named Shakespeare lines. That's a list of strings. And it is the result of calling read file and giving it ./Shakespeare.txt. And then we'll print Shakespeare lines. All right, and we get the empty list. Okay. So we need to talk about this argument for just a moment, right? So let me actually annotate this for just a second. So notice we're calling read file, this function that we defined right above. And here, we're giving a file name, right? So this is the file name string that we're hoping to provide. It's just a string. So what's going on here? Well, you'll notice that this is a little bit different than the examples we've used in the previous lesson. And there are some conventions around file names and expectations, specifically this // that are a little bit beyond our concerns, more than we need to know for right now, but just to give you a sense of what this actually means. This dot means in the same directory, right? So right now we're in this file named shakespeare.ipynb, and if we look in that same directory, we should also find this file named shakespeare.txt. And so this is how we use a string, what we call a file path, to refer to a file in the same directory. Of course, if we wanted to read a file from our data directory, we would have to say, okay, look up one directory, and then go into the data directory, and then go look for another file. And you separate those things with slashes, and you'll see that in the next exercise. So again, a little bit beyond our concern, but that's what this sort of funky-looking // is saying. Look in the current directory for a file named shakespeare.txt. All right, and we see that the empty list is produced because we still have more work to do. Whenever you want to work with a file, the first thing you need to do is actually open it. And this was true when we were working with CSV files. It's going to be true when we're working with text files as well. So the file that we're going to open with is, or we have a file handle. Its type is a text IO wrapper. And we're going to open the file name string that we were given as an argument. And we will open in a certain mode that is read mode. Okay? If we wanted to be very pedantic, if we wanted to be able to read files that had things like emoji or foreign character sets, we could say encoding is UTF-8, right, as one last option. We don't actually need that last option, encoding UTF-8, for this example because we're just working in a plain text file. It's all just plain characters. But if we had, as I mentioned, emoji or character sets, such as hiragana, katakana, and so forth, we would need UTF-8. I want to spend just a moment talking about this string R. It feels like a magical string, and it kind of is. If you were to hover over this function open is a function that's built in at the top level of Python, just like min, max, list, dict, and others. And if you scroll way down, you see that there's, and if you were to read this, you would see that there are a few different modes you can open a file in. When you're writing a program, you can say, hey, give me a file that I can write to, that I can save data back out to, or that I can read from, or that I can open in binary mode. Maybe I'm working with photos or sounds or videos, and some other options as well. We're trying to just read a file in loop to loop over each line in it. Kind of like in a CSV where you can loop over each row. Here we're going to loop over each line in the file, but it's just going to be a string, and that string will be the contents of that line. Right, so we can write for line in file. And what are we going to do with this line? Well, we're going to append it to our lines list. So lines.append line. And if I rerun this, and I actually encourage you maybe to not rerun this quite yet. Let's actually not rerun this. Let's print length of Shakespeare lines, right? So if you printed Shakespeare lines directly, you would have a list of 124,000 strings in it trying to show up in your Jupyter notebook, and sometimes that can make VS Code a little bit sad. You're working it very hard, but here we're just printing the number of lines we read in, and what we've got are 125 or 124,000 lines in this list of strings. You can be sure that we would never ask you to diagram something like this, but if you can imagine what a diagram would look like for this, there's a lot of data that our program now has access to that's sitting in memory that we can work with. Because it's unwieldy to look at that much data, I want to show you a new piece of syntax that is pretty Python specific that allows us to see just a certain range of data. So we can print Shakespeare lines. And what we're going to use here is something called a slice. So if I just used a regular index like 0, what we would see printed out is this is the 100th eText file presented by Project Gutenberg. If we were to choose line, if I were to go find what's the very first line of this file that actually has Shakespeare's works in it, I think it's not down to like line 200 something. Yeah, 1609, this is, and the sonnets, 247. All right, so 247 minus 1, 246 is the sonnets, right? So this is the first line in that file that we can see. And if we wanted to see the first 5 lines, you can actually use a colon here and say 246 to 251, say. And this is what we call slice notation. We're taking a slice of a bigger list, and it allows us to say, okay, between these indices, give me a new list that has just those items in it from those indices. And it's a nice way of looking at a subset of a list. This isn't something that works in many other programming languages. It's very Python specific, so that's why we don't emphasize it much, but it is handy in a scenario like this. So right out of the gates, you're probably noticing something kind of strange about this, right? We've got new line characters, the /n that we learned about way long ago. You probably, it's probably a faint memory at this point that /n means, return a new line and start a fresh new line. And this character is like a hidden character at the end of every line of a text file. And that's what causes text to not wrap. So if I press the backspace, somewhere, or press enter, that's what that \n is doing in the text. You don't see it. It's what causes a new line to exist, though. But we probably don't want that in our data. We don't care about new lines. We're already separating each item. So one of the things we can do is actually pre-process our lines just a little bit. So within the for-in loop, before we append, let's change line. So line is reassigned to line.strip. And strip is like stripping paint from a wall, right? So what we're doing here is we're saying take any spaces, including new line characters, from either end of a string, if there are spaces at the beginning of the string or spaces at the end of a string, and just strip those away so that you only have the text that's in the middle of spaces. So spaces, tabs, new lines, anything like that is what gets stripped away when you use this strip method of a string. Most languages have something like this that's often called something different, like trim in another language. But yeah, it's a common feature of a string that you might want to strip away the white space that might exist on either end of it so that you just have the text in the middle. The next thing we probably want to do, because ultimately our goal is to count lowercase letters, is to convert all of our uppercase letters to lowercase letters. And so we can say line is assigned line.lower. And lower is a method on all strings that converts uppercase letters to lowercase letters. So now we see, okay, we're getting a little bit closer. And maybe if we wanted to avoid having lines that were just empty strings so that all that we had left were lines that actually had text in them, we could add an if statement here to do something like if line is not equal to the empty string, then append that line to lines. And let me actually choose a range that's like 0 now. And we go back to the top, all right? So we've removed new lines, and we don't even have to print anymore. We've actually got 114,000 lines of text left after we removed 10,000 lines from this work, right? They were just empty. You can imagine other kinds of pre-processing, like there's some lines in here that are just the years and dates, but we're not going to worry about that for our purposes. We're good to go. So the next thing we want to do is actually we can pause here for a moment, and let's just pause here and make sure that to the best we can, we've got this example running where if we print the length of these number of lines, we've got 114,000 lines or so. And the TAs can come around and help if you're stuck, you couldn't get this file saved. If you did get it working, check in on Course.Care, and we'll keep moving in another 3 or 4 minutes. Hey, hey.
Oh, how do you get the entire web page to copy? Everything
Sure.
else makes sense, but the simplest thing is not what I got.
2 more minutes, and then we'll keep moving. If you want to respond on Course.Care by clicking the plus button next to the message in the discussion, that'd be great.
Getting like a different number than the
I should mention that if your line count is a little bit different, it should be fine. If it's in the 100,000s, that's all we need for today's example. All right. So let's continue on. And I should also mention that if for some reason, especially once we get to the part where we're plotting with a chart, if for some reason you're running into errors, don't stress. We can help you in office hours. And just following along conceptually is totally fine too. So let's add another markdown cell here. And in this markdown cell, the point of what we're about to do is, OK, now that we have a list that has every line of text in this text file, in this body of work, let's go and count up all of the letters one by one. So let's say the next step of our analysis is to count the letters in the lines list one by one to find the frequency of use of each letter. All right, so this will ultimately tell us things like are S's used more than T's, or E's used more than V's, things like that. And how many times was each letter used? Before we implement this algorithm, which wouldn't be that bad to implement, I want to pause and turn it over to you for a hands-on function implementation where let's actually just write down what it is that you're going to do. So our goal is to define a function named tally. And the purpose of tally, and actually you'll notice that I'm still in markdown mode. You can tell by the bottom right of this box here saying markdown, and we actually want this to be a code cell, so I'm going to change this to a code cell using the ellipses button. And now these are just Python comments. Right? So we're going to define a function named tally, and we're going to give the function as params, or as parameters, a dictionary reference, key is string, and value is int, and a key. If the key is in the dictionary, increase value by 1. Otherwise, set keys value to 1. Right? So the point of this function is it's going to be a little helper function. We're going to give it a dictionary that's going to contain the counts of the tallies of everything we've seen prior in a key. And all it's going to do is take a look and say, hey, have I seen this key before? If so, I'm going to increase its value by 1. So I'm going to tally up one more count of the letter J, the letter C, the letter P, right? Otherwise, if it's the first time we're seeing a letter, like T or H, we're going to enter a value of 1 and continue on from there. So see if you can implement this function. And I should also mention the return type. It is a procedure and returns none. Right? And we'll talk about the implications of this. This is an example of where references are kind of handy. And the fact that we're able to pass something by reference, this dictionary, and modify it, mutate it, it will come in handy. So let's spend about 5 minutes on this and see if you and your neighbors can implement this together. 2 more minutes on this. And this is just a helper function. We'll have one more that actually counts all the letters up. All right. So this is just a little helper function that our main algorithm is going to wind up using. Because anytime you're counting in a dictionary, you typically have this problem where you have to test, oh, have I seen this key before? And if so, increment it. If not, start it off with a value of 1. So I can define my function tally, and it has 2 parameters. You could have named yours whatever you'd like. I might name mine counts is the dictionary, where the key type is string and the value type is integer. And the key that we're counting is a string. And there's no return value in this function. This is a procedure. And you're probably thinking, what's the point of a function that doesn't return anything, but it's supposed to have some impact? Well, this is one of the examples where using a reference can be handy. We're giving a reference to this dictionary, counts, and we're actually going to mutate that dictionary. We're going to change something about it. We're going to increase or add a new key value pair to it. So then what we're saying is if the key is in counts, right? So if key is in counts, what we're going to do is increase that key by 1. Right? Else, we're going to set it to 1 and introduce a new key value pair. Right? So you should have had an implementation that looks something like this. And again, what we're doing is we're testing, does this key already exist in counts? Have we already seen the letter A? If so, let's add one more to A's tally. And if not, let's say, okay, A, we've seen it once now. And we'll use this as a helper function in the next function that we're going to write that actually carries out the goal that we're trying to achieve here, which is let's count up all the letters in everything Shakespeare ever wrote. So the next function that we'll implement is count letters. And we'll work on this one together up to a point, and then I'll turn it over to you. And actually, let's add a docstring for good measure to tally. I shouldn't have skipped over that. So the docstring here is mutate counts to increment a key by 1 if it exists, or initialize to 1. Right? And that could probably be written in a little bit more concisely, but it describes the point. And if you wanted, you could delete the comments above it that set up the function. So with count letters, what we're trying to do is we're trying to give it a list of all the lines of text that we read in from this Shakespeare file. So let's set up a parameter for that. So lines is our list of strings. Right? And what we're trying to do is return and produce a dictionary where our key type is going to be the character or the string, and our value type is going to be an integer, the count. Right? And the point of this function is count frequencies of all letters in a list of strings. Now once again, because this function says that it returns a dictionary where the key type is string, value type is integer, we don't yet have a valid function. This isn't a skeleton of a function yet because there's no return statement in here that returns the correct type. So let's go ahead and set up our variables so that we can make this a correct but not, or a valid but not necessarily correct function. So counts is a dictionary where key type is string, value type is integer, and it's initially the empty dictionary, and we return counts. All right. So before we fill in the blank there, one of the things we can do is we can actually set up a variable to store this result and then print the result and see that we've at least are getting an empty dictionary here. So let's go ahead and set up a variable named Shakespeare letters. And it will be a dictionary from string to integer that is initially assigned count letters. And what are we counting? Well, remember in the previous cell up above, we set up a variable named Shakespeare lines, and that's the list of strings that had every line in that file. So Shakespeare lines. Cool. And now if we print this variable, so print Shakespeare letters, we see the empty dictionary. Right? So we're almost ready to implement this algorithm to count up all the letters in this file. This is going to be one more exercise where I turn it over to you all, but the goal here is to loop through all of the lines in our list of lines, and then for every line we're going to loop through all of the characters in that line, and we're going to count it up and count it into this variable that we set up, and we can use this tally function to help us. So we're going to loop through all lines. For each line, loop through all characters, tally character into the counts dictionary. Okay. And if you want a challenge, tally only letters, no numbers or punctuation. All right, so if you finish the first 3 lines of looping through all the lines, looping through all the characters in a line, and then tallying those characters into the counts dictionary using your tally function. If you get through all that, you can try taking on the challenge of only tallying letters up. But if you don't get to that, that's okay. Let's spend a few minutes on this, and the TAs can come around and help, and you can work together. If you've correctly implemented this, when you print this out, you should see a dictionary literal that has letters as all the keys, and then integer numbers is the number of times that letter was found in our file. 2 more minutes on this, and then we'll work through it together. Twenty more seconds on this, then we'll work through it together. All right. So this is something we could do with while loops, but this is an example where for-in loops work very well. And the reason for that is because we're trying to traverse the entirety of a collection from the start to the end, right? So we're going to loop through all lines from the very first line to the end. And then for every line, we're going to loop from the very first character in that line all the way to the very last one. And for that type of a pattern, for-in or for-each loops are very handy. So for line in lines, that takes care of looping through all of our lines. We can then say for character in line, right? So the line, each time that outermost loop runs, it's being updated to be the next line of text in our giant list of 100 and some thousand lines. And then we're moving through each line in that, or each character in that line one by one. And what we're trying to do is make use of this tally function. So we're tallying. Counts is the dictionary that we're giving as a reference, and the key is this character that we're counting up, right? And so this 3-line incantation is saying, hey, go through every line in this file, go through every character in that line, and tally up that character into our dictionary of counts. This feels kind of funky because we're not doing anything. We're not saying any new variable is being assigned the result of tally. But this is one of those examples where passing something by reference is actually handy, right? We're saying, hey, I'm giving you a reference to my counts dictionary. You can change that, and that's OK. We're both going to be referencing the exact same dictionary. And that's how we're going to keep a tally without having to do a bunch of returning and going back and forth in that way. All right? So if I evaluate this, we'll see that it took 2 seconds to move through every single character in Shakespeare. And we see that the letter T was used 329,000 times. The letter S 248,000 times. But we're seeing some things that we wouldn't have expected in here as well, such as the question mark was used 10,000 times. I think last class I saw the exclamation mark was used 8,000 times. So there's more questions than excitement in Shakespeare. And we probably just want the letters, right? So how do we actually narrow this down? Well, we can do some more filtering here. So in this for loop, we could say if character is greater than or equal to the character A, and character is less than or equal to the character Z, we can tally it up in this way, right? So we do one extra conditional, and we test, and we be sure that we're only dealing with letters, right, between A and Z. And we can use string comparison to do that. And sure enough, now we've narrowed it down to only the letters that were in Shakespeare. Okay. I want to point out, because we saw some string methods earlier, such as strip and lower. Strip removed the white space from the ends of a list, or from the ends of a string, and lower converted everything to lowercase. It turns out it's pretty common you want to be able to test whether a string is made up of only alphabetical characters. And so we can test if char.isAlpha for is alphabetical, and this method on the string will return true if it's an alphanumeric character or false otherwise, which is effectively the same as what we just did. But this would also work with uppercase letters, whereas our test was only lowercase, but that's okay because we'd already changed everything to lowercase. All right? So here in the span of, we've been together for less than 50 minutes, we've written a program that when we run it, if I were to run from top to bottom, so I run all, we see that, in under 10 seconds, we read the entirety of Shakespeare's body of work into memory, and then we counted all of the letters, how many times they occurred throughout that work. And if you imagine trying to do that work as a human, the tediousness and how boring that would be and how long it would take you and how many errors you would make in that process, this is where you start to really feel some of that computational power. And having a file that's 120,000 lines long is still pretty small by today's standards in terms of processing data. But nevertheless, it's something that we can, we've all had to read a play or two at some point. We've been subjected to the misery of Shakespeare. Sorry for any Shakespeare lovers out there. And we only read small parts of it, and it was still very difficult and time-consuming. And we can write programs to process this type of textual data much more quickly. Now, we're still not to a point of being able to visualize this data, right? Like we can reason about this a little bit. Like the letter Z is used very infrequently relative to the letter T. But it would be nice to have a visualization of this. Before I move on to visualization, is there anything about what we've written so far? Any questions on what we've written so far? All right. Feel free to drop them in chat as well. So let's add one more markdown cell here. And I'm going to use my plus markdown button. Before I do this, I have a bad habit of this, and I would encourage you to try and not also have this bad habit. When I'm working in a Jupyter notebook, I tend to forget to save the notebook. You'll notice that white circle in my tab saying I haven't saved recently, or I've made changes since I last saved. Control S on Windows, Command S on Mac. As you're working on the next exercise and you're working in Jupyter notebooks, you do want to be saving pretty frequently, and you definitely want to save before you submit for grading, because if you don't, what you submit for grading will be wherever the last time you saved was. So you may have actually run a lot of code and made a lot of progress in a notebook, but we don't see it on the grading side because you didn't save. So be in the habit of saving your Jupyter notebooks with frequency. So this last markdown cell is going to be, let's create a visualization of this data with a bar chart. All right. And I'm going to set up a new cell below that and make it a code cell. So to create a visualization, we're going to use a library called matplotlib, short for Mathematical Plotting Library. So from matplotlib, import pyplot. Right? And pyplot is a module within this library that if I try running this, you'll see that I get a green check and I don't have any errors yet. If for some reason you have errors, know that it's not uncommon. It means that at the very beginning of the semester, there may have something that gone wrong in the install. We're missing this package called matplotlib. Come by office hours, we can help get that installed and be sure that you've got it. We just need to install this library on your machine using pip, which was a program we used earlier. But if this ran, that means we can start to try and plot our data. So let's try adding a title to our plot. So pyplot.title, frequencies of letters. Right? And if I evaluate this, you'll see that we've got a chart that doesn't really have any data in it. It has no axes labels or anything like that. We still have more work to do, but we can see that we've added a title to a chart, and we're starting to make some progress. One of the things I'll note is that when we're working with a library like PyPlot, there's a lot of different methods and functionalities, and typically whenever you want to go and graph something, you have to go look up, search the internet, find people who have graphed something similar on Google, or find an example that you did previously, and reproduce those. These are things that you don't tend to memorize. Like I couldn't do this without having done it recently, when you're working with large libraries, you tend to use the reference to figure out and remember how to do things. So the next thing that we'll do is we'll add an X label, so pyplot.xlabel is going to be our letters along the x-axis. All right, and pyplot.ylabel is going to be our frequencies or counts. All right, so if I reevaluate this cell, can't quite fit. There we go. You can see that we start to get labels on our axes, and we still need to actually go and grab the data. So when we're making a bar chart, we need both a list of the labels for each of the bars as well as a list of the values for those bars. Currently, all of our data is in this dictionary named Shakespeare letters, right? So one of the things we can do is we can ask a dictionary for its list of keys and for its list of values, and that will give us the ability to have our labels and values for our bar chart. So let's set up a variable named labels that's a list of strings. And it is the result of asking the Shakespeare letters, I believe is what we called it. Let me just double, yep, for its keys. And we're going to turn this into a list using the list constructor. So why we needed to use the list constructor here to say, hey, construct a new list of Shakespeare's letters keys is the type of asking a dictionary for its keys isn't actually a list as we know it. It's something that's kind of like a list. It's a sequence. But we wanted to just have a list here, and so we're converting it to a list ourselves. Similarly, with our values, we will have values be a list of ints. And this will be the list of Shakespeare letters.values, right? And if we wanted to convince ourselves that this was correct, we could print labels and print values. And if I reevaluate this, you'll notice that when we printed out the labels, those are just the list of letters, and then that list of values that we've set up, and those were the keys of our dictionary, and then we have the list of those values, which are the corresponding quantities of each letter found in our analysis. So last but not least, we actually need to set up the bar chart. And to set up the bar chart, you just need these two lists. So we would say pyplot.bar, labels, and values. Right? Cool. And we have a chart that has the frequencies visualized for each of these letters. We'll notice that the letters aren't sorted. We'll come back and deal with that problem in just a moment so that we have them alphabetical. But right out of the gates, we can see that E is the most common letter. Z looks like the least common letter, followed closely by Q, J, and X. Right? So maybe you could use this to inform Wordle guesses. But actually, with Wordle, I'll show you where you can get the list of all possible Wordle words, and you can run it through the same program instead of Shakespeare's works and get the actual distribution of letter frequencies in 5-letter words that are valid in Wordle. Cool. So we've seen two new things here, not just the charting, but the ability to ask a dictionary for its keys and its values. The last thing we want to achieve is actually sorting these things so that we get alphabetical, so we get this in alphabetical order. In order to do that, I want to add one more code block. Let's see, how do we? So if you hover in the area between the last markdown block and this and the code block, I'm going to add one more code block here. And I want to talk, this is going to take us on a little bit of a tangent to talk about something called a tuple, which will help us sort these keys and values. So the first thing I want to show you is, and then we'll come back and talk about exactly what we're doing. We're going to say items in dictionary is a list of tuples where the key type is string and the value type is integer. And it's the result of asking Shakespeare letters.items. Oops. And we need to convert this into a list as well. Right. And if we print this, what you'll see is something that will start to tell us what is going on with this idea of a tuple. And we're going to actually swap out to slides that we skipped over a few weeks ago and talk more directly about what a tuple is. But here you probably have a little bit of intuition, right? Where, let me make this a little bit bigger. We're asking this dictionary for its items. So what is an item? Well, an item in a dictionary is the pair of a key and a value. And that's actually a tuple. So a tuple is a way of grouping multiple values together, and they don't have to be the same type. So notice our tuple is a type where the first element is a string and the second element is an integer. And items gave us a list of these things once we converted it to a list, where we have a list of these pairs, right? So we have a list of tuples, which are, in this case, a pair of a string and an integer. And this is kind of neat, because now we have a list of values, and Python has a built-in way of sorting these values, which we'll see in just a moment. Right? So that where we're going with this is we're going to be able to sort this list, and then we're going to be able to turn it back into a dictionary, which will then finally allow us to visualize all this data in alphabetical order instead of in the order in which we encountered these characters. So let's talk briefly about what a tuple is, and zoom out to think about sequences in general, because a sequence is a tuple is a special kind of sequence. So what is a sequence? Well, we've talked briefly about this. It's an abstract data type where we have an ordered zero-index collection of values or set of values. And that should actually more correctly say collection of values. And examples we've seen include a string, right? This is a ordered sequence of character data, right? A list is a dynamically lengthed or dynamically sized sequence of values that can be different values of the same type, but you can have lists that hold different types of data. What we're looking at very briefly today, which is kind of specific to the Python language, there are other languages that have similar capabilities, but not quite as prominently as Python, is it's a fixed size sequence of values of any types. So like a list, we're saying we're constraining you to the same type of data. With a tuple, we can have a string and an integer, or a string and a float, or a string and a float and an integer. You can combine and mix and match. You can also have 3 integers, 3 floats. But it's fixed in size. So once you set up a tuple, you can't change anything about it. It's immutable. And we looked briefly at the idea of a range, and we may come spend more time with that later, but today we're just thinking about this tuple. So there are some examples down at the bottom, which I'll get to in just a second. But again, it's a specific fixed length sequence that can mix types. So when we specify the type of a tuple, that's a tongue twister. We can say tuple, and then in the brackets, what are the types of each index? Okay, so for example, we typically want to name these things. So often we'll set up a new type, like say the type point2d is going to be a tuple where we have 2 floats together. And this is how you would represent a point in a 2D space. And you could use this type then as a variable. It's a type of variable. So notice origin is of type point2d. And the way that you specify a tuple literal is with parentheses rather than square brackets for list literals or curly braces for dictionaries, right? Similarly, you could imagine color. When you represent digital colors, you typically model them as a combination of red, green, and blue. So 3 different values, how much, what percentage red, green, and blue, or what magnitude. And here we can imagine the color gray is a tuple of 3 integers, 128, 128, and 128. If you've done any web development, you've seen similar ideas in representing color. Additionally, we could imagine setting up a player type of tuple where we have string as the first item index and float as, or it could have been int. I should have had 5.0 in the example down below. And we can combine different types like this all right? So coming back to our example, you'll notice that if we ask a dictionary for its items, we get back a list of tuples, or we get back tuples that we can turn into a list. But we really want to sort these things, all right? So maybe we can say items in dictionary is the result of using Python's built-in sorted function, items in dictionary, right? And so if we print that, you'll notice what it did was it actually went through and sorted these tuples by the first item in them and sorted them alphabetically by default in ascending order, so from A to Z. This sorted function has other ways you can use it. You can get things in descending order. You could use this for a list of integers, a list of strings, a list of floats, and it would sort those values in that list for you. It also works, as we can see, with a list of tuples, which is pretty cool, right? So here's that list of tuples sorted, and now what we want to do is actually say, okay, let's set up a new dictionary. Sorted letters is a dictionary from string to int, and it's the result of constructing a dictionary from the items in dictionary. And we can print sorted letters. Oops. Cool. And I'm actually going to remove that print items in dictionary line so that we can actually see this all in one go. All right. So just like you can ask a dictionary for its items, which is a list of tuples, you can give the dictionary constructor a list of tuples, and it will reconstruct a new dictionary for you with all of those key value pairs in them, as long as your tuples had only 2 items in it. And so here, that's what we did. So now notice we have a dictionary where all of our keys are sorted. If you're feeling like, wow, that was a lot of steps to remember how to sort a dictionary, the good news is if you need to actually do this in the future, you Google it, and you find examples of how to sort a dictionary in Python by its keys. I did that earlier today because I had forgotten how to actually carry out these sequences of steps. But what we broke down here was this way that we could deconstruct a dictionary, take its items, rearrange them, and then reconstruct a new dictionary to be in a better place. So we can bring this home by, rather than using Shakespeare's letters or Shakespeare's keys and values for our visualization, we can instead use sorted letters keys and sorted letters values. All right. And when let me see if I can get this a little bit smaller so it fits. There we go. And so now we get a nicer visualization where our keys are actually sorted in the way that we would expect them to be, A through Z, and we can see the different magnitudes of each letter in this body of text. Right? I mentioned to you earlier that you could also, I'm going to open this up in the side here. If you were to go to bit.ly/wordle-words, so wordle-words after bit.ly, let me make this a little bit bigger, you would see a list of, I'm not sure how many items in this list there are, but it's all the 5-letter words that are valid in Wordle. And so you could copy this data in, and I'm actually going to do this for demo purposes. Probably, I might make a different file here. So rather than shakespeare.txt, I would maybe make a new file, wordle.txt, and paste. And you don't have to follow along with this as I'm doing it here, but just to show you that this is possible, set up a new text file. And if I go back up to the top, rather than using shakespeare.txt, wordle.txt, I replace out my file name in my program. I run it all again. We see that there's almost 13,000 valid words that you could use in Wordle. And we go down and we see the distribution. And it turns out Wordle has a much different distribution than Shakespeare. So in Wordle, the letters that you would want to use are A, E, S, O, and R as the most frequently occurring in 5-letter words. Right? So I'll leave these last few lines that we entered here. And any questions on what we've done here so far? So just as a quick recap, today was an example of taking the tools that we've come to know and love, functions, dictionaries, lists, foreign loops, and apply them to a particular problem, which was how do we process textual data. And here we broke it down to just how do we count characters up. But the thing that I hope you're able to feel and appreciate sort of the magnitude and the power of is taking, hundreds of thousands of lines of text or 100,000+ lines of text today and writing a program that can analyze that in under a few seconds once we've got the program written and can be applied to different textual data sets for different types of analyses. Similar types of analyses are done in natural language processing. One of the most common, how autocorrect works is very similar to this. It's keeping a track of pairs of words or sequences of words that you're writing in your phone, keeping track of those as counts and using those counts relative to one another to try and predict what is the word that you're most likely to type next. And that tends to be what one of the key heuristics autocorrect uses to choose the next word as you're typing it out. With that, I think we're all set for today. I hope you all have a wonderful spring break. Get that reading turned in, and we'll see you in a couple weeks.